These are the notes for AP Calculus on the topic of the second derivative test. So remember, the first derivative test was to determine where a function has local minimums and maximums, and we found the first derivative, found where it's 0 or undefined, and drew our number line and tested. The second derivative test is an alternate way to do that. So it says if f prime of c at some specific x value, the first derivative is 0, and the second derivative at that same c value is greater than 0, that would mean it's concave up. Then what this would look like, first derivative is 0, so like right there, that would be the c value we're talking about. At that c value, it's concave up and has a slope of 0. You can see that would make this a local minimum at that specific value. Similarly, if first derivative again at that c specific x value c is 0 and the second derivative is less than 0, that means it's concave down there at that specific value c. So what this would look like, some c value here. If the function is concave down with a slope of 0, it would look something like this. So concave down, then you can see that would be a local maximum at x equals c. So let's take a look at how we can use this in practice now. It says find the x-coordinates of any local extrema, in other words local minimums and maximums, using the second derivative test where applicable. And justify your answer using the second derivative test where applicable. Okay, so it starts off like the first derivative test. You got to find your critical numbers by finding the first derivative, which would here using the power rule would be 12x squared minus 10x plus 2. And in this case it won't ever be undefined, so just set it equal to 0. You can factor out the 2 with GCF, and that leaves you with 6x squared minus 5x plus 1. And then to see if that factors, it's a trinomial here, so you can find factors of 6. And we want the sum to be negative 5. Let's see what would work there would be negative 3 and negative 2. Multiply to be positive 6, add up to be negative 5. And then we can use those two to split up the middle term. So we'll have 6x squared. Instead of negative 5x, that's the same as negative 3x minus 2x. And then leave the plus 1 on. And then you split it in half and group factor it. So the GCF of the first two terms would be 3x. And when you factor that out, what we'd be left with is 2x minus 1. And the GCF of the second two terms, well, there's nothing except leading term is negative here, so you'd have to factor out a negative 1. And that would change the sign of both of those, so it would become a positive 2x and a negative 1. And now you can see both of these have a 2x minus 1, so you can factor that out like the GCF. And then the other factor left, what's left would be 3x minus 1. And then we still have the 2 out in front equals 0. So now we can see what our critical numbers are. Well, the 2 can never be 0. If you said 2x minus 1 equals 0, you'd get x equals 1/2. And if you said 3x minus 1 equal to 0, you'd get x equals 1/3. So those would be our critical numbers. So these are the only possible x values where we might have a local minimum or a local maximum. So so far it's been just like the first derivative test. If we were using the first derivative test, then we would draw the number line and test to see where the first derivative is positive or negative in between on the different intervals with using 1 and 1/3 on the number line. But with the second derivative test, we find it in a different way. So now, going from right here There's our first derivative. Let's go ahead and find the second derivative. And use the easiest form. In this case, that's going to be easier than the factored form, in which case, if you took the derivative right here, you'd have to use the product rule. So the second derivative here is, using the power rule, 24x minus 10. And what you do is you just substitute these in one at a time to see the concavity. So let's go ahead and plug in 1/2. F double prime of 1/2 will be 24 times 1/2 minus 10. Well, 24 times 1/2, that's 12. Minus 10 is 2. So since that's positive, we know the graph is concave up. And we already know the slope is 0, because that's where we got this. We set the first derivative equal to 0. So that would make it a local minimum. So we can say, because it said to justify our answer, we can say f has a local minimum at, and it only asks for the x coordinates, so that would be at x equals 1/2. And then your justification would be since, well, there's two aspects to the second derivative test. It's the first derivative has to equal 0 at 1/2, so f prime of 1/2 is 0, and the second derivative f double prime of 1/2 in this case was positive, making it concave up. Now let's look at our other critical number of 1/3, and let's also substitute that into the second derivative. So f double prime of 1/3 would be 24 times 1/3 minus 10. Well, 24 times a third, 3 gives them 24 8 times, that's 8 minus 10 is negative 2. So since it's negative, that means at 1/3 the graph is concave down, shaped like a frown. And since we know the slope is 0 this time, at that value there has to be a local maximum. So then we can say f has a local maximum at x equals 1/3. And your justification would be since f prime of 1/3 is 0, the first derivative is 0, and the second derivative f double prime of 1/3 is less than 0. Okay, let's take a look at another example now. So on this one, to find the first derivative, here because we have x times 2x minus 1 cubed, that's where we need to use the product rule. So using the product rule to find g prime of x, take the derivative of the first one, derivative of x is 1, times the second one as it is, 2x minus 1 cubed, plus the first one as it is, which is x, times the derivative of the second one, using the power and chain rule there, would be 3, 2x minus 1 squared, times, using the chain rule, the derivative of the inside function, 2x minus 1 is just 2. And again, to figure out where this is 0, find our critical number, let's set it equal to 0, and notice we can factor out, if you think of this is like your first term here, and this is your second term. Notice what they have in common is they both have a 2x minus 1, and this one has a lower exponent of 2. So we can factor out a 2x minus 1 squared. And then let's see what we have left of each term. Well, this one just had the 2x minus 1 cubed. We factored out 2 of those already, so there's only 1 left. Plus, this one we factored out all the 2x minus 1 squareds, so all that's left is x times 3 times 2, so 6x. So we have 2x minus 1 squared, and combining like terms, that becomes 8x minus 1. So now in that factored form, we can see the only way that can equal 0 is if one of those is 0. So if you set 2x minus 1 equals 0, you get x equals 1/2. If you set 8x minus 1 equals 0, you get x equals 1/8. So those would be our critical numbers. And then you would, if you're using the first derivative test, you put on the number line, but here we're going to use the second derivative test. So here the easiest place to find the second derivative is probably from right here after we simplified it. So we still would have to use the product rule again though. So g double prime of x, second derivative, would be the derivative of the first one using the chain rule there and power rule. So that would be 2x minus 1 to the first times the derivative inside is just 2 times the second one as it is, 8x minus 1, plus the first one as it is, 2x minus 1 squared, times the derivative of the second one is just 8. And we just need to figure out at 1/2 and 1/8 if this is positive or negative using the second derivative test. But it might be easier to simplify this. You don't have to, but I think it will be easier if we do that. So let's look at, here's like the first term, those are all multiplied together, plus here's the second term. So let's see what those have in common. We could take that as a GCF. So notice this one has 2 times 2 is 4, this one has an 8, so we can factor out a 4 out of both of those. And they both have at least 2x minus 1. This is to the first, this is to the second, so factor out to the lowest exponent of 1. And then what we have left, well, what's left of the first term, the 2's and the 2x minus 1 is gone, so all that's left is that 8x minus 1. Plus, here we're left with a 2x minus 1 because it was squared, and 8, we factored out 4, so there's a 2 left. So left with 2. And we're left with 2x minus 1. So we've almost got it simplified all the way here. So we've got 4, 2x minus 1. And let's see, if we distribute out that 2, this would become 4x minus 2. Combined with the 8x minus 1, 4x and 8x gives you 12x. Negative 1 and negative 2 is negative 3. And if you want to make it even simpler, now notice you can actually factor out 3 out of that times the 4 that's already out there. It would be 12. 2x minus 1. And after you factor out the 3, all that's left is 4x minus 1. Now it'll be easier to tell if it's positive or negative each of these values. So let's try 1/8 first on this one, see what happens. So if you plug in 1/8, again, all we're concerned with is whether it's positive or negative. So if you plug in 1/8 here, 2 times 1/8 is 1/4 minus 1, that's going to be negative, times 1/8 here, 1/8 times 4 is a half minus 1, that's also negative. So negative times a negative is positive. That means the graph is concave up. So at 1/8 we've got a local minimum. And then when we test 1/2, when you test 1/2, well, what happens when you plug in 1/2 right here for x, 2 times 1/2 is 1 minus 1 gives you 0, which multiplied by everything else wipes out the entire thing. So here is where, if you get a 0 when you plug it, a critical number into the second derivative test fails here. And if it fails, all that means is you got to revert back to the first derivative test. So let's go ahead and do that. But it won't be too hard because we already know there's a local minimum at 1/8. So first derivative test, remember you just draw your number line. And we'll label it g double prime of x. Our critical numbers were 1/8 and 1/2. Those both made second derivative 0. And notice we've already know there's a local minimum in the second order test at 1/8. So in order for this to be a local minimum, it would have to be changing from, first derivative has to be changing from negative to positive. So the graph would be decreasing to increasing. So all that's really left is to test one more interval. Oops, and sorry, this was not g double prime, this is supposed to be g prime. So this is the first derivative test. And if we test like 1 here, it's going to be this factor. Well, that's always positive because we square it. And we plug in 1 right here. 8 times 1 is 8 minus 1 is positive, so it's positive right there. So notice at 1/2, the first derivative doesn't change sign, so it's not a local minimum or a local maximum. It just keeps on increasing, which is oftentimes why the second derivative test fails. Not always, but it oftentimes fails because it's neither a local minimum nor a local maximum. So to just help, we only have a local minimum on this one, so we can say g has a local minimum at x equals 1/8, and your justification would be since g prime of 1/8 was equal to 0, made the first derivative 0, that's how it was a critical number, and I figured out the second derivative, g double prime of 1/8 is greater than 0. So on these two problems, second derivative is really just an alternate way of finding your local minimums and maximums. The first derivative test would have worked on these also, as we can see right here. Give you the same information in a different way. However, there are some problems where the second derivative test is a little bit more necessary. And that's on these implicit differentiation problems. So the first one says, consider the curve given by x squared plus 4y squared equals 12 plus 2xy. Find all the points where f of x has a horizontal tangent line. Okay, so remember, to have a horizontal tangent line, like that, that would mean the derivative, or slope, would have to be 0. Slope of a horizontal line, remember, is 0. So we need to find our derivative on this one. Using implicit differentiation, so this is not a function because the x's and y's are all mixed up in it. So we take the derivative of x squared is 2x plus the derivative of 4y squared is 8y. But remember, whenever the variables don't match up with what you're taking the derivative with respect to, in this case x, you have to here multiply it by dy dx. And then equals, well, the derivative of 12 is 0. And then when you take the derivative of 2xy, there you need to use the product rule because we've got 2x times y. So the derivative of 2x is 2 times y as it is, plus derivative, the first one as it is, 2x, and times the derivative of the second one. Derivative of y is just 1, but then again we took the derivative of y term, so that's where we need dy dx. And then remember, you get all the terms that have dy dx on one side if there's more than one, and then all the terms that don't have dy dx on the other side. So I'll leave this 8y dy dx here and subtract over the 2x dy dx. And then on this side, I'll leave the 2y there, and then I'll subtract the 2x over there. Because what that allows you to do then is to isolate the dy dx so you can factor it out. Leaves you with 8y minus 2x. And then what you can do to solve for dy dx is just divide by 8y minus 2x. So then the derivative, dy dx here. Now you can do a little simplification because you notice you can divide the numerator and denominator by 2. That'll just give you y minus x over 4y minus x. And if we want to find a horizontal tangent where the slope is 0, well, that would come from setting the numerator equal to 0. If you wanted a vertical tangent line where the slope is undefined, then remember that's where you'd set the denominator equal to 0. So here when you solve this, you just get, if you add over the x, you get y equals x. And then remember what you always have to do on these is take that and substitute it back into the original equation. Because it also has to be a point on this curve here. So here you can either replace x with y or y for x because y equals x here. So I'm going to substitute in an x everywhere there's a y back in the original equation. So that'll give me x squared plus, instead of y, 4x squared equals 12 plus 2x times, instead of y, another x. And now let's simplify this and solve it for x. So x squared plus 4x squared is 5x squared. Equals 12 plus 2x times x is 2x squared. Then if you subtract over the 2x squared, you get 3x squared equals 12. Divide by the 3. So x squared equals 4. And take the square root of both sides. You get x equals, square root of 4 is 2, but don't forget whenever you take the square root of both sides, you need that plus or minus. So plus or minus 2. So there's actually two x coordinates, 2 and negative 2, that will work here, that will make the derivative 0, so we'll have a horizontal tangent line. And then you just plug them back in the simplest place, right here, to find the y coordinates. So here, if x is 2, y is 2. So that would be one of our points, 2. And if x is negative 2, y is negative 2. So when x is negative 2, y is also negative 2. So those would be the 2 points where f has a horizontal tangent line. And then, in part B, it says at each of these points, determine if possible whether the curve has a local minimum or a local maximum. So because our first derivative is in terms of x and y here, not just x, can't really use the first derivative test, but we can still use the second derivative test. So starting from right here, we can take the derivative of that. So the derivative of our first derivative, which was dy dx, equals y minus x over 4y minus x. Okay, and here we'd have to use the quotient rule. So the derivative of the first derivative here is the second derivative. And using the quotient rule, we take the derivative of the numerator. So the derivative of y is dy dx minus the derivative of x is 1 times the denominator as it is, 4y minus x, minus the numerator as it is, y minus x, times the derivative of the denominator. Derivative of 4y is 4, and then that's where we need the dy dx, minus the derivative of x is 1. All divided by the denominator as it is squared. And then we just need to find, normally what you'd have to do here is substitute in the dy dx for both places to get it just in terms of x and y. But here, all we're concerned with is that our points 2, 2, and 2, negative 2, negative 2, whether the second derivative is positive or negative. So there's some little shortcuts we can use when we do that. So now let's find the second derivative, specifically at the point when x is 2 and when y is 2. So the reason why we don't have to plug in to our first derivative here is because we know both of these points make the first derivative equal to 0. So the first derivative is going to be 0 here, minus 1. And then we'll plug in 4 times y is 2, minus x is 2. Minus, well, when you plug in y minus x, that's the same as the numerator of our derivative. And remember this, when they're both 2, that's going to make this 0. That wipes out the whole term there. And then the denominator, we don't have to worry about it because it's just squared, so that's always going to be positive. So really all we're left with is negative 1 there, times 4 times 2 is 8 minus 2 is 6. So we get negative times a positive is negative. If it's negative, we know the graph is concave down. And that means since it's concave down, we've got a local maximum there at 2, 2. So we can say 2, 2 is a local maximum. And let's do the same thing with our other point here. The second derivative specifically when x is negative 2 and y is negative 2. And we can use some of the same shortcuts. Makes the first derivative 0, just like this point did. Minus 1. 4 times negative 2 minus negative 2. Minus, again, when you plug in the same thing, y minus x, that's just going to be 0. And you have negative 2 minus negative 2. So that wipes that whole term out there. And again, we don't have to worry about the denominator changing the sign because it's squared, so that would make it always positive. So here we've got a negative 1 times, that's a negative 8 plus 2, so that's negative 6. Negative times a negative, this time it's positive. That means it's concave up. And so that means our other point, negative 2, is a local minimum. Okay, let's look at another one where we need a second derivative test. Another implicit differentiation one. But this one, it says let y equals f of x be a function that contains the point 0, 2 and has a slope given by dy dx equals xy minus 3x. So here they're already giving you the first derivative. And determine whether this point is a local maximum or a local minimum and justify your answer. So the first thing we have to do is figure out if this is a critical number or not. So the point we're given 0, 2 here, when x is 0 and y is 2, doesn't make the first derivative 0 or not. So when you plug in 0 for x, 2 for y, you see in fact, okay, that is 0. So that means it's a critical number. So it could potentially be a local minimum or local maximum. So again, to see which one it is. Again, because our derivative is in terms of x and y, we don't know any other points here, we can't use the first derivative test. So let's use the second derivative test here and find our second derivative by finding the derivative of the first derivative. So the second derivative, derivative of the first derivative, do the second derivative, would equal, here to take the derivative of xy, we need to use the product rule. So the derivative of x is 1 times y as it is, plus, first one x as it is, times the derivative of y is dy dx. And then the derivative of negative 3x is negative 3. And again, all we're concerned with here, you could substitute in the first derivative here, but all we're concerned with is whether this is positive or negative at the point, in this case, 0, 2. So we've got y there, so we've got 2 there for y. Plus, x is 0. So that wipes that one out. And the derivative is also 0 at this point, so it's like 0 times 0 there. So that wipes that whole thing out, and then minus 3. So we end up with 2 minus 3, which is negative 1. Since the second derivative is negative, we know it's concave down. And we already know the first derivative is 0. So that's going to be a local maximum this time. So we can say that f has a local maximum at 0, 2. And this one says to justify your answer. So it's like the ones we justified before, just the notation is different. So using the second derivative test, since the first derivative, which was dy dx, specifically when we plugged in x equals 0 and y equals 2, the first derivative was 0, and the second derivative, again when we plugged in x equals 0 and y equals 2, that was negative, less than 0. And that concludes the notes on the topic of the second derivative test.